Here we see the AC input represented by the sine wave. As this current passes through the converter, the negative half of the waveform is removed, resulting in a rectified output or DC. By introducing a controllable element like an SCR, we can control when the rectifier starts conducting. This delayed conduction allows us to fine-tune the power output based on the system's needs, making it ideal for applications like motor speed control and voltage regulation. In this half-wave non-controller rectification, the mean value of the DC output, shown by the red line, represents the average voltage we get from this rectifier. This output can be used for simple DC applications but is not very efficient due to the large ripple and low mean value. Now, when we introduce controlled rectification by using an SCR or delaying the conduction, the mean value of the output decreases. The controlled rectifier only allows current to flow for a shorter portion of the cycle, which reduces the overall DC output. Hi friends, my name is Ron, and this is Power Dumped. In this video where we explore how an AC-DC converter works, we'll take you step by step through the process of converting alternating current into direct current and understand the key components that make it possible. In this RL circuit, we're focusing on the behavior during the positive half cycle of the AC input. As voltage rises, the resistor dissipates energy, and the inductor stores energy. This results in the output voltage across the load, shown here as the positive half of the sine wave. Now let's focus on the negative half cycle of the AC input. During this phase, both the current and voltage reverse direction. The inductor, which stored energy during the positive half cycle, now releases that energy, while the resistor continues to dissipate it. This process results in the negative half of the sine wave as shown on the right. Before we dive into how the circuit behaves, let's take a moment to understand the role of the diode. In forward bias, when the voltage at the anode is greater than the voltage at the cathode, the diode begins to conduct. Essentially, it acts like a closed switch, allowing current to flow freely from anode to cathode. This characteristic is what makes the diode so useful in controlling the direction of current in circuits. In reverse bias, when the voltage at the cathode is higher than the anode, the diode acts like an open switch, blocking the current flow. This is how the diode prevents current from flowing in the reverse direction. Now that we understand how a diode behaves, let's take a closer look at how it functions in an RL circuit. We'll see how the diode allows current to flow during the positive half cycle and how it blocks the current during the negative half cycle. During the positive half cycle, the diode is forward biased, allowing current to flow through the RL load. The output voltage, shown in the waveform on the right, follows the positive half of the AC input, creating a positive half-wave rectified signal. During the negative half cycle, the diode is reverse biased, and current is blocked from flowing through the RL load. However, the inductor, which resists changes in current, generates a negative voltage peak. This is due to the back EMF produced by the inductor, as it tries to maintain the current flow, resulting in the observed negative peak. Now let's talk about the bypass diode and its crucial role in protecting the circuit. The bypass diode is designed to provide an alternate path for the current when certain conditions are met, such as when the main diode is in reverse bias. This helps maintain a smooth flow of current and protects sensitive components from voltage spikes, especially in circuits with inductive loads. Essentially, it ensures the circuit continues to function without interruptions, even under varying voltage conditions. Let's take a closer look at how it operates within the circuit. In the positive half cycle, the main diode is forward biased, allowing current to flow through the RL load. At this moment, the bypass diode is off because it is in reverse bias. The current flows through the main diode, and we observe the normal positive waveform in the output. During the negative half cycle, the main diode is reverse biased and blocks the current flow. However, the bypass diode is now forward biased and allows current to flow through the RL load, bypassing the main circuit. This prevents current from returning to the source, as it now follows the path provided by the bypass diode. At this point in the circuit, the output voltage is zero because the bypass diode is in reverse bias, preventing current from flowing through the main loop. As a result, the inductor and resistor cannot generate any significant voltage across the load. The bypass diode takes over, redirecting the current away from the load, effectively bringing the output voltage down to zero. But how can we control the output voltage in the circuit? Well, that's where the SCR comes in. An SCR, or silicon-controlled rectifier, is a semiconductor device that controls the flow of current. It operates similarly to a diode, but with a key difference. It can be turned on and off using a gate signal, allowing precise control over when current starts flowing through the circuit. For the SCR to conduct, the voltage across the anode and cathode must be forward biased, meaning the anode voltage must be greater than the cathode voltage. In addition to the forward bias, a gate current must be applied. This positive pulse to the gate is what triggers the SCR to turn on, allowing current to flow from the anode to the cathode. Once the SCR is triggered, it remains conducting as long as the current through the device remains above a certain threshold, even after the gate signal is removed. The SCR will turn off only when the current through it falls below a specific level, typically at the end of a half cycle of an AC signal. Let's observe how the SCR behaves in an RL circuit with a bypass diode. In the positive cycle, the output voltage remains zero until a gate pulse is applied, which triggers the SCR and allows current to flow. During the negative cycle, the SCR is reverse biased, meaning the voltage at the anode is lower than the cathode. In this condition, the SCR naturally blocks any current flow, and the output voltage remains at zero. Even if we apply a gate pulse during the negative cycle, the SCR will not turn on because it is reverse biased. The SCR only responds to gate pulses during forward bias. Thus, in the negative cycle, the output remains zero regardless of any pulse. Now let's ask an important question. How does the firing angle control the output voltage? The firing angle, denoted by alpha, is the angle at which the SCR is triggered during the AC cycle. By changing the moment the SCR receives the gate pulse, we can control when the current starts to flow through the circuit. This is crucial because the later we trigger the SCR within each cycle, the less time we allow current to flow. This directly reduces the average output voltage. Conversely, if we trigger the SCR earlier in the cycle, the output voltage will increase as we give more time for current to flow. Let me show you how this works with different firing angles. Here you can see that when the firing angle is 0 degrees, the SCR conducts for the full cycle. The output waveform follows the input sinusoidal waveform with no delay, allowing the full voltage to reach the load. This means the output voltage is maximized. Now, as we increase the firing angle, say to 45 degrees, the SCR starts conducting later in the cycle. Notice how the output voltage is now delayed, and as a result, less voltage reaches the load. The average voltage decreases. This concept continues as we keep increasing the firing angle. By controlling the firing angle, we can precisely manage the output voltage from the AC source, allowing for effective control of power delivery to the load. When the firing angle is set to 180 degrees, the SCR never conducts, and the output voltage becomes zero. This is because the SCR does not receive a gate pulse in time to conduct before the cycle resets. As we've seen, the SCR allows us to control the flow of current in a circuit. But what if we wanted to control both the positive and negative halves of the AC waveform? In the next episode, we'll explore how to control a full-wave rectifier using 4 diodes and delve deeper into controlling the entire AC signal. Thanks for watching. I hope you enjoyed learning about the basics of rectification and how we can control and convert AC to DC. Don't forget to like, subscribe and hit the notification bell so you don't miss the next episode. See you next time.